So we are going to discuss chapter 8 this time, and it is about what we call LTI systems. And LTI stands for linear time invariant LTI systems, and we're going to talk a little bit more what that actually means. And related analysis, which is convolution, correlation, and coherence. So what is an LTI system? Let's kind of consider one. And as you can see by the color, this is a black box. And this black box actually is a linear time invariant system. And let's kind of kick this system and look what comes out of this system. When you have an LTI system, just like any other system that responds to input, you can have some kind of a stimulus, and that will give you some kind of a response. In that sense, the LTI system is not unlike any other system. The interesting thing about an LTI system is that when you have, let's say, a stimulus that is, I say now capital S, which is kind of a multiple of the little s, then actually the response will also be a multiple of the little r. And basically these are features that we call superposition or scaling. Superposition means if I have response x1 giving, or sorry, stimulus x1 giving response y1 and x2 giving response y2, then superposition tells you that if I give it a stimulus x1 plus x2, then my response will simply be y1 plus y2. So it's a very simple system. And scaling means it's related to this, of course. If I have some constant times x1, it will give me some constant times y1 as output. That's called scaling. And if the system kind of obeys these two rules, it's linear. If it violates any of them, it's nonlinear. The time invariant thing means that if I have some stimulus xt leading to response yt, that when I give the same stimulus but at a different time, it will give the same response but also shifted in time. That may seem trivial, but some systems basically vary over time. This system doesn't vary over time. It gives you exactly the same response tomorrow as it did yesterday, provided, of course, that the initial condition is the same. If you change the initial condition, it will be varied. So, and this is the time invariance. So this part is the linearity, and this part reflects the time invariance. And if they have both properties, it is a linear time invariant system. If it violates one of these two, it is a nonlinear time invariant system. Right? But for now we are still going to look at linear systems until probably after the midterm, then we start to think about nonlinear systems. And of course the neuroscience systems are usually nonlinear. But to understand nonlinear systems, if you do not understand linear systems, it's pretty difficult. So for that reason, we start at linear systems. And as a matter of fact, it is surprising how much you can even understand in neuroscience by just applying linear systems theory. And it's also amazing to me that many people kind of go to these difficult models, whereas if they had gone to a simpler one, they might have been able to explain the same phenomena. And simpler is usually better. Huh? Another thing is you have different types of systems even within the LTI systems. You have, for instance, dynamic and static systems. That means that a dynamic system has some memory, whereas a static system does not. And in the book, I'm not going to go into the detail here, but in the book I give you an example in figure 8.2. And in figure 8.2 you see actually one system where we have two resistors in series, and whenever something happens in the potential in the battery X, it will be immediately affected in the output of the system, which is the potential over one of the resistors. And so there is no memory, it is instantaneous, and that's a static system. If you replace one of the resistors for a capacitor, that is actually, you can use that as a simplified version of the membrane model of Hodgkin and Huxley that you probably have heard of. This would be a simplified version of that. Then there is a little bit of memory in the system, and the system becomes dynamic. And as soon as the system is dynamic, we have to describe it with differential equations. If the system is static, you don't need differential equations. Another difference in system that is playing a role frequently is systems that are causal versus non-causal. And most systems are actually causal, which means that they respond to current or past input and not to future input. Physical systems usually do not respond to future input. Of course, you can always pretend, if you simulate a system, that it responds to make up future input, but real systems, physical systems don't. I mean, if I could do that for the stock market, I would be filthy rich, if I had a system that could respond to the future. So most systems are actually causal, and most interesting systems that we actually look at are dynamic, which means that we have to describe them with some kind of a speed involved in the equation. And if you have speed involved in the equation or acceleration, then you have a differential equation. Now, I started to say, well, if you have some kind of a basic stimulus and a basic response, then you can easily derive what a stimulus is that is a multiple of that, because it would be just a multiple of that response. So if we had to pick a simple stimulus, do you have any idea what would be an handy stimulus to pick? Yeah, the delta. Yeah. So I would say that if you give it the delta function or the unit impulse, that is a very nice basic stimulus, because from the delta function you can basically reconstruct any other function, which is nice. And we will do that in a little moment. The system will then respond to what we call the unit impulse response. And as we will see, once you know what the unit impulse response is of a linear time invariant system, once you know that, you basically know the whole system, and we will see that in a little bit. I don't know if Albert came to the point last week, but if you actually do the Fourier transform of the delta function, you could also see that it contains all the frequencies, because the Fourier transform of a delta function is simply 1 for all frequencies. So it is constant, it contains all the frequencies. So that's another way of explaining why the delta function is such a handy choice. there are a few basic equations for the dynamic and causal systems. You have this one. You have basically a set of terms with different levels of derivatives. So the n means the nth derivative, and the n minus 1, the n minus 1 derivative. And this one is the function itself, so not a derivative. This is the output, and this is a same series for the input. And you will see that any equation that we derive for an LTI system will satisfy this. Of course, in many cases, many of these A's and many of these B's are 0. And if all of them are 0 except A naught and B naught, then we deal with a static system. If one of them is actually includes a derivative, it's a dynamic system. In discrete time, so this is for continuous time. In discrete time, we can do something similar. And again, you see it is a series of terms of the output y and a series of terms of the input x. And y and x are basically with different delays, varying from n to 0. Same thing here for the input, varying from m to 0. I forgot something here. This should basically, of course, also include multiple terms. So. So let us get back to our LTI system, where we have input x and output y. And let's look at a simplified version of how it would be if we offered this system a combination of unit impulses. And what I'm going to project now is figure 8.3. So we have here, if you look at the the top line. Here we have the input, and then here we have the output of this system. And in this case, we start with some input like a unit impulse response, and in order to keep it usable for a little bit later, we just change variables. We instead of time t, we use now tau for time. And let's say that we offer it a delta function delta tau. And we offer that delta function there, and then we get an output, basically that is h tau. Huh? And in this case, h tau is just a rectangle, just to keep it simple. It doesn't really matter how that happens, but this is some system that if it gets an impulse, it creates a rectangular signal. Now the next thing you can see, and that is kind of a characteristic of the time invariance of the filter, that if I give him the same impulse, and that would be delta t minus tau, or tau minus t, because the delta function is even symmetric, so tau minus t or t minus tau gives you the same thing. For now you will see in a bit, it's handier to write it down as t minus tau. So again, this is my time scale tau, and now I have a unit impulse at time t. And since the system is time invariant, I will get the unit impulse response shifted by time. So this is the time invariant property, isn't it? And you can actually see that in the second line of this figure. You can see that if I have this pulse, it would give me this rectangle, but if it gives me the blue pulse here, it would give me the same rectangle, but it would be shifted in time. The next thing I can do is I can take the same unit impulse here, but instead of having it at unity, I'm going to give it some weight. So I'm going to say give it a weight that is determined by some function x tau, and this is the delta function, so this is a weighted delta function here. The delta function tau is now weighted by x tau. And now the output, as I may expect according to the scaling law, will be a unit impulse response that is also weighted by tau. So that is the scaling property, isn't it? And that is something you can actually see in the line here. You can see that this one, although it's also shifted, but ignore now for the fact that it is shifted, this is twice as big, and you can see that it gives you a square wave that's also twice as big. Now if I would also shift this thing, it would basically let's say that I'm going to shift this to this spot here. Now I would get the same response, but it would be shifted in time, which would be again the time invariant property applied results into. So here I am combining the scaling with the time invariance. So the fact I'm using the scaling because it's a linear system, and I'm using the time invariance because it's an LTI system. Yeah.
For the last thing you wrote, why is it x of tau and not of x of t minus tau?
Oh, okay. Yeah, if you take, do you recall the shifting property? Where you had, let's say, t and t minus delta. Well, just pretend that I replaced tau for t and t for delta.
Okay.
And then you basically sift out that part of the whole response. So now what you can see, and that is the part of a linear system that we call superposition, is that if I give the system a combination of pulses, like in this case I give it 2 pulses, I can just say, well, if I know what is the response on one, then basically these two are just going to be superposed, and then when I do superposition here, this will be the total response. See? And here I have even a more complex one. Here I have a unit impulse shifted and weighted by the factor of 2. A unit impulse that is shifted 2 units, a unit impulse that is shifted 3 units and multiplied by 1/2. And for each of these unit impulses, I can basically describe what the responses are going to be, because I know what the unit impulse response is. And then I add them all up, and then I will know what my total response is of the system. So that's basically what a linear system is. Very, very, very simple. Now, if I apply that to this superposition to a continuous system, then instead of an addition, I will get an integral. I can say, well, I'm going to make my steps really, really fine. So instead of superposition using addition, I'm using an integral. So if I use the superposition here, I can get that for the input. And I get that for the output. So I'm just adding an integral for input and output. And since we go over the delta function, you can integrate from minus infinity to infinity. Same here. You can integrate from minus infinity to infinity. Now we have to talk a little bit about these limitations, because if we had to characterize the system from minus infinity to infinity, we would have to be very old. And I know I'm a lot older than you guys, but still not old enough to go to minus infinity. And so basically what you usually do is you pick some time that is convenient, that everything is at rest, and then you say, you know what, instead of going from minus infinity, I'm going to go from a time 0. The other thing is that, and we just mentioned causal systems, the other thing is that since the system is causal, anything that is beyond the point t, which is the point where this thing occurs, everything that is beyond that in the future is not going to affect the system. So I don't have to go all the way to infinity, because what happens after t is inconsequential. The system doesn't know that anyway. And so for that reason, this part is often replaced by t. So you see both versions of this equation. You see it from minus infinity to infinity, and we will use that every now and then when it's convenient. But when you are really consistent and you are really doing tests, you often go from 0 to t. Of course, if you assume that everything beyond 0, back from 0 and beyond t is 0 anyway, then it doesn't really matter which one you pick. So this basically gives us the following result. It gives us, for this system, that output y is is this. And this is the convolution integral. So this is convolution. And there is a short way of writing this as well, with this little x with a circle. So you see that it's used for different things in different papers sometimes, but usually when you see something like that, they mean convolution. And now you see basically what I just said in the beginning, which is that, well, once I know what the unit impulse response is of this system, I basically know the system. Because once I know ht, I just have to convolve the input with h, and I know what the output is. So that's all you need to know from a linear system. That's not true for a nonlinear system, but for a linear system, this is what you need to know. So now we know how to use convolution to get to a linear system. It can be actually practical to consider this convolution in the frequency domain, which is what we are going to do next. And you will see how practical that can be. So we're going to look at convolution in the frequency domain. How do we do that? We basically say, well, we take the Fourier transform of the convolution of two functions. Let's just take x times h. We just had that, so let's take that one. I think in the book I do x1 and x2, but that doesn't really matter. So now we apply the Fourier transform to the convolution. So in between the square brackets is the equation we just derived for the convolution. And outside the square brackets, you have the Fourier transform as you have seen it a lecture ago. So I just do now the Fourier transform of the convolution. And as you will see, that simplifies stuff. It may not look that way currently, but it does. We are going to change the order of integration. And that will give us I will do my best to write the difference between t and tau clearly, but kind of keep an eye on that. So now I basically put the convolution one outside the brackets, and I put the Fourier transform inside the brackets. And since x tau is not a function of t, I can take that out of the integral. The next thing I'm going to do is I'm going to change variables. And I'm going to use capital T as t minus tau. just notice that because of that, lowercase t is capital T plus tau, and dt lowercase is dt uppercase. Right? That's these are the consequences. And now I'm going to plug that in to this expression. So first, I wrote down the equation for the Fourier transform of the convolution, and I basically wrote it completely out. Then I changed the order of the integration, and next I changed the variables. And now I'm going to plug that into that equation. So what do I get? And now I'm going to look only at the expression between the brackets. That'll give me h capital T, because t minus tau was capital T. Then the exponential is little t, so that I can replace by t plus tau. And if I have t plus tau there, basically I can write it as a product of two exponentials, isn't it? So I can write that as e minus j omega, tau. Let's do it actually different. That makes it easier. J omega capital T times e minus j omega tau. Because the little t was capital T plus tau. And now I'm writing it as a product. And then d little t is the same thing as d capital T. So this is only the expression between brackets, isn't it? And since exponent of minus j omega tau is not a function of capital T, I can move this thing over here, isn't it? I can get it out of the integration sign. So I can write this as e minus j omega tau times, and what is the rest of that expression? When I move e minus j omega tau out of the integration sign, do you recognize what the remainder is of that expression? Yeah, it's the Fourier transform of h, isn't it? Yep. So now I'm going to plug that in. The whole expression here, because this was just a piece between brackets. And then I am getting, I'm going to kind of use other brackets to avoid confusion. See? And what is the expression now between the first brackets now, between the left brackets? It's again the Fourier transform, but in this case it's the Fourier transform of x, isn't it? And here you see what I started to say at the beginning. It makes actually things easier. Because if you have to do the convolution of two functions, you have to do this sometimes awful integral. If you happen to know, and sometimes you don't, but you can use tables to find them. But if you happen to know what the Fourier transform is of each of them, you don't have to do this awful integral. You can just multiply it. And then at least you have the result in the frequency domain. If you then want to have the result in the time domain, you could kind of transform it back, which can be awful too, but there are lots and lots of tables to help you there. So sometimes it's actually easier to solve such a thing, not always, but sometimes it's easier to solve this thing in the frequency domain and use tables to do the transformation, or do the transformation yourself, instead of doing this convolution. And as a conclusion, you could say that basically if you have the convolution of x and h in the frequency domain is just the product of x and h. And then I'm using capital X and capital H for the Fourier transform, and the lowercase x and h for the time domain. And with that double arrow, I just mean to say that it is a Fourier transform pair. And so they belong together. So now we are ready to look at the next topic, which is very related to convolution, unless there is a question about convolution before we move on. No. So correlation, I think, to some extent you know it's if you think about autocorrelation, which is the correlation of a function with itself, if I just plot xt versus xt, I get this thing, isn't it? Just a straight line. And because I plot the same values against the same values, and the correlation is 1. What autocorrelation is also interested in is what happens if I plot xt at time 1, so xt1 versus xt2. That sometimes gives you, as we will see, very interesting and very useful information about the system. And if x is the same signal, it is called autocorrelation. If you have an x and a y here, then it is a cross correlation. And we will actually use cross correlations intensely to analyze nonlinear systems, but it's also very useful to look at linear systems. So what will this correlation look like, for instance, if I have noise? Truly random noise. Yeah, not really, huh? On the average 0, yeah, but if I take random noise, I basically probably get something like this, isn't it? It's all over the place, and on average, indeed, it will be 0. Yeah. There won't be, unless, of course, T1 is T2. In that case, you will get that. So it's interesting that the autocorrelation function of noise is non-zero if T1 and T2 are equal, because then there will be 1. But it is 0 for all other cases. See? You have any idea what this would look like if it was a periodical system, periodical signal? Of course, in this case, it will be also, and every time that I shift it a full period, it will be like this. But everywhere in between, it will start losing that correlation. So the correlation, depending on the shift, will depend on how much you shift it. And if you shift it a full period, it will be 1 again. So let's kind of look at the autocorrelation function. It's usually indicated as RXX, T1, T2. XX meaning the same signal X. So if it's the signal Y, it would be RYY, of course. And then T1, T2 to indicate that you have different, and of course that can be then expressed as an expectation. The product of X at 2 different time moments. That's the most generic definition of the autocorrelation function, or sometimes abbreviated ACF. Very rarely people will use this. So it's the most generic definition. But most of the time, you will assume that this thing is stationary. So in that case, the only thing that's of interest is the time difference between T2 and T1. Because it doesn't really matter at what time you are starting, because if it's stationary, you can pick any time. So in that case, you can write it as if it is stationary. You can already see that there is some similarity rising between this and convolution, because here we have t plus tau, and here we had t minus tau. So there you see some similarity already popping up. The next step you can do is say, well, we're going to assume, or we're going to show that the system is ergodic. And if it is ergodic, I can change the expectation for a time average. And in that case, I would have this equation. And now I have a time average. The cross correlation is basically working out the same way. There's not much difference there. In that case, I do not have x and x, but I have x and y. And so we have rxy at 2 different time steps, or 2 different moments in time. And that is in the most general way similarly defined as the expectation of the product of the two at the 2 different instances of time. And if you assume stationarity and ergodicity, then it's often kind of shown as this. And notice that in this case, just as you guys did a few lectures ago with the Fourier transform, we just moved out to 1 over t because this thing, of course, is inconvenient if you do that. But then you have this as a cross-correlation integral. If you look at it in discrete time, very similar. It's like that. And again, if we assume stationarity and ergodicity, we can use the time average as well. And now we don't have an integral, but on a sum, of course. This is, by the way, the equation, sometimes weighted with some factor, but differently. But this is the way that MATLAB under the hood computes the cross correlation, or one of the algorithms. In addition to cross correlation, we sometimes talk about cross covariance. And just as that you have the moment and the central moment, the cross covariance is the cross correlation where the signals are demeaned prior to. So there's a little difference. Actually, I would recommend that whenever you look at cross correlations or autocorrelations, that you demean your signals, unless you have a special reason not to. Because your DC component in your signal, certainly in neuroscience, usually doesn't mean a whole lot. Except when you're looking at resting potentials, of course, then it's important. But in general, it's not too important. In MATLAB, these are the two commands, xcor for the correlation and xcov for the cross covariance. Of course, you don't need xcov because if you do xcor on your demeaned signal, it's the same result. You get exactly the same. And I have you do some homework stuff on that, on an example. And maybe we should look at one of the programs. If you start up MATLAB, then we can run one of the programs. And that program is showing you what the cross correlation is of this, in this case, the autocorrelation, I think, of this one. So this is a discrete dynamical equation. As you can see, this satisfies the equation we started with all in the beginning. It has a number of yn terms, in this case just 1, and a number of xn terms, in this case 3. And one of the things that is used often is looking at these things when x is, for instance, a random time series. And this is an example you can read about on pages 138 to 139. And that's also the example that is shown in program 8_2, which we are going to look at now. if you run this program, it will compute using the random command in MATLAB the output of that time series and then look at the correlation. And what it then computes is the correlation versus the delay. So here is the shift. So you have one shift, two shifts, etc. in number of time points. You have discrete time. So you can shift it with 1 point, 2 points, 3 points, etc. -1, -2, etc. And then basically when you do that, you see that most of the time the autocorrelation of y is close to 0, except in this area. And on pages 138 and 139, we actually, I'm not going to write that up in the blackboard, but you can read that. There is actually shown in that table and also in the text how you can make a prediction of what that is. And of course, when you then simulate it with random time series, you get very, very close to that prediction. And every time that you simulate this thing, your outcome will be a bit different, of course, because you use a random time series. So maybe even on your screen it looks a little bit different than on mine. That could very well be. That is the reason. So, and the thing is that the reason that this is relatively easy to deal with is that when you use the expectation notation, you can then, by looking at the expectation of yn versus yn plus m, you can, when you write yn as the expression of x, you can take advantage of the fact that the expectation of x is only non-zero when n is equal to m. And so for that reason, one of the things you should do, and as a matter of fact it's also part of your homework, you should test yourself and see if you can kind of follow this prediction. Another thing that I want you to look at home is the frequency domain aspect of the correlation. And since the expression for correlation and convolution is so similar, the derivation that I just showed you for convolution in the frequency domain is pretty identical to the expression of the frequency domain of the correlation. Recall that for the convolution, the frequency domain expression became the product. So if I have convolution of x and h, that became the product of the Fourier transforms. If you do the same thing for the auto or the cross correlation, well, let's do the autocorrelation now. For the cross correlation, it's pretty similar. We'll do that in a minute. It's also a product, but in this case, because of the difference in sign, because in the convolution it was a minus sign, and now we have a plus sign there in the autocorrelation and cross correlation. In this case, it's also the product, but this star indicates the complex conjugate. And you can read this on page 140. If you understood the part that we derived for convolution, you should have no problem reading the part for this. The real interesting question is do you recognize this expression in the frequency domain? Because this is time domain, cross correlation. This is frequency domain, cross correlation. Does this ring a bell? That's the power, yeah. It's the power spectrum. It's the unscaled power spectrum, but indeed, so cross-correlation in the time domain basically is directly equivalent to the power spectrum in the frequency domain. So it's the unscaled power spectrum. And this is called the Wiener-Kindchen theorem. Well, similarly, if you have the cross-correlation instead of autocorrelation, it gives you the cross spectrum. That's what it's called. So this is often called the power spectrum or auto spectrum. And if you do the same thing for two different signals, it's called the cross spectrum. Now the auto spectrum, I think you guys looked at that. The auto spectrum, by definition, is a real number, isn't it? Because it just works out that way. Yes?
That's d tau or dt?
Oh, let me ask you this. What do you think it is?
Well, I thought it would be dt.
Yeah, that's absolutely correct. And so I kind of wrote it very unclear. Thank you.
Okay.
Yeah, it has to be dt because the cross-correlation is a function of tau. And you can never have that, your integration variable can never survive the integration process. So you're absolutely correct. So now what was I saying? Because now you... No, it's fine. So I was talking about the cross spectrum, and we were talking about the fact that this thing was always a real number. Of course, the cross spectrum can be real, but is usually a complex number because it doesn't always work out that way that it gets real. Usually it doesn't. And believe it or not, that's a good thing because we are going to use that in the last part that we are going to discuss, which is the coherence. Because with the coherence, we take advantage of that. So, coherence. What is coherence? You can read all about it on page 142, etc. Just let's look at what we are actually trying to do. Let's say that we have two signals, x and y. And at some point, we are just going to cut this signal in pieces. Let's say we start here, and we keep going, and we stop there. So then we would have 1, 2, n epochs of signals x and y. Now let's say that for every epoch, I'm going to compute the auto spectrum of X. And for every epoch, I'm going to compute the auto spectrum of Y. And I'm also going to compute the cross spectrum of X and Y. So these two are the auto spectra. And this is the cross spectrum. These guys are real. This thing is complex. And the other thing I can do is, and you will see that this is the whole purpose of the whole exercise, is since Sxy is a complex number, I'm going to determine what the phase is of that complex number, which is basically the inverse tangent of the imaginary divided by the real. So for every Sxy, I'm going to just look at what the phase is. So and now I'm almost there. Now what I will do is I will take the average over the n epochs, which I indicate with these triangular brackets. And sometimes you will see an n with a bracket to indicate that it is averaged over n epochs. Some people just don't mention that. And now I'm going to compute, or basically use these I'll use the same color. Tara would be so happy I'm using all the same colors now. Oh, that's true, it's not pink. Yeah. So I'm going to determine this coefficient, and to make it so, because here you can see that I have the product of two spectra, so in order to make the dimensionality correct, I'm actually going to square this, and I also take the absolute value. And this is the coherence. So this expression is the coherence between x and y. And you can follow the math a little bit, but this thing will normalize to 1. And as a matter of fact, what I have been doing is, by this coherence, is that I'm just showing you what the average is of all these phase plots. That's what it boils down to. Because for xy, I just took the average, so I took the average phase. I normalized it all to 1. And so that means that I basically show you the average of all the phases in the unit, on the unit circle. So in this case, the end result would be something like this, isn't it? if I would add up all these vectors, I would get something that looks like this. Suppose that x and y were both noise. What would you expect? Would you agree if they were both noise, I would find a vector pointing this direction, pointing that direction, pointing the other direction, pointing in all directions. And then if I average them, my result will be 0 or close to 0. Theoretically, of course, if I have an infinite number of epochs, it would be 0. Now, of this result, there are two things that you can look at. This is the coherence, which is the size of this phasor. That's the coherence. See, this is the absolute value, so that's the size. You also have phase coherence, and that would be the angle. It doesn't happen often, but sometimes papers will tell you what the phase coherence is. If they do that without telling you what the coherence is, it may mean nothing. Because if I take two traces of noise and I average it with a finite number of epochs, it may have a very low coherence number, but the phase coherence by definition will also be some finite number. And so if people tell you, oh, the phase coherence is so many degrees or so many radians, you always have to ask them, and so what was the coherence? Because if the coherence was really a small number, you're very close to noise. That coherence has to be a significant number, otherwise the phase coherence doesn't mean anything at all. That's an important. So let's. Oops. I just dropped my. I think it's still on. Let's look at an example with program 8.3. Advertising a new version of Java, which I'm not interested in at the moment. So if I do program 8_3, I basically get the output of a coherence analysis using the coherence by hand and using the standard coherence command in MATLAB and comparing the two. It's always a good idea if you try to understand something to compare what MATLAB does with what you do, and that's shown in figure 1. The stuff that we computed by hand is the red dots, and the black lines connect the part that MATLAB's command does. And this basically shows you what really happened. Here you see the red dots. These are basically the phase and the coherence values for each of the 3 segments, and then this is the resultant of that. So, and let's look at a listing of this program. Kind of try to open this. So there it is. If you look at the program, basically the top part shows you the three replications of signals x and y, and they're not exactly the same. Then in the next one, the signals are combined into a single signal. That's in the signals combined header. Then I use the cohere command, which is actually an old command in MATLAB, but it still works, to compute the coherence between x and y. And then I'm going to do it by hand, using our recipe that we just discussed. And there you can see that the first part is the FFTs, which is happening here for all the x's, the FFTs for all the y's. Then we compute the power spectra and the cross spectra for the individual trials. And then finally, on line 54, we compute the equation that we just had on the blackboard. And the absolute value of the mean of pxy, the mean is the average, squared, divided by the mean of x, power spectrum of x, and power spectrum of y. And then the results are plotted. And one result is plotted against the standard MATLAB routine, and the other one is showing you the polar plot of the individual phases. So that's what this program is doing. You can actually really nicely apply that to analyze EEG and to look at, for instance, if you have signals and you want to know what frequencies are leading, what frequencies are lagging, you can use this to analyze signals in a multi-channel recording, for instance. And in epilepsy, for instance, it's always important during a seizure to see which one is leading and which one is lagging. That's one application, but there are many of them. And in this figure here in the book, in figure 8.5, that's the one that is not very clear in the black and white version, unfortunately, but you could download the color one from my website. But here you can see an 128 channel recording reflected with the different dots, and then these different colors indicate who is leading and who is lagging, and that kind of can help you in saying, well, these frequencies are basically originating from this area, and other frequencies may be originating from other areas or the same area, which would kind of point home that a particular area is the culprit in initiating the seizure. This is actually a picture from one of my colleagues, Dr. Toll at the neurology department. So this was recorded in one of our patients in the past. Now, another very important aspect is using all this in the spatial domain, and my graduate student, Jo Suresh, who is sitting there, has done that. She was going to show you some of this, but considering the time, we're going to kind of move that to the next lecture. So she's going to start and show you some of the applications that she has done and that she has used in analyzing her pictures. Because the same thing, of course, what can be applied to time series very often can be applied to spatial information. Any questions before we stop? If not, I'm going to give you your homework.